Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today will be the last week in which I will actually introduce new material. This is the end of the language models lecture. And next week we'll have a celebration. So we'll have a final quiz, we'll go through the semester, what we've learned, and celebrate the end of the semester. I will talk about the exam, what to expect. But before it comes to that, we will finish the material today. I might even have time to ask you a few clicker questions at the end if time permits. I hear from Georges that the mystery game is ongoing. We already have 2 submissions that are correct. So it means you have 1 more chance to win a prize. So you should try. The goal is to relate some documents to the corresponding embedding in the vector space and to find out which belongs to which, right? Okay. So where were we? We were in the middle of language models, but not the large ones, the small ones. The large ones, they are going to be introduced in a different course. And I have to just go back where we were. So first, this is where we stopped. I threw at you all of these very complicated formulas, which basically are based on the chain rule. It's the idea that for a document to be a document, we need to have a lot of things happening. We need for it to have at least 1 word. We need for the first word to be a specific word. Then we need to have a second word. Then we need for the second word to be a specific word, and so on. And for these kind of things, we can use the chain rule, which is the idea, for example, with 3 variables, that probability of ABC is the probability of A times the probability of B conditioned on A times the probability of C conditioned on A and B, right? And we get a chain rule. So of course, now it's more than 3. It's actually way, way more than this. So we had this huge formula originally, but then we made a few assumptions. And this formula that you see right here has a few assumptions. One assumption is that the probability of having 1 more word is always the same, whatever the length we already have. That's 1 minus p stop, right? So we have a probability of p stop of stopping and a probability of 1 minus p stop of not stopping, right? So every time I have to check that I don't stop already at the beginning, then the probability that the first word is D1, then I don't stop, then the probability of having D2 conditioned on D1, then I don't stop again, 1 minus p stop, then the probability of D3 conditioned on the first 2, then again, the probability that I don't stop, and then the probability of D4, but here you notice something, I only have the dependency on 2 and 3, that is because of the Markov rule, because we lose information when it's too far away in the past, we only remember the previous 2 words, in that case, because we take 2 as the parameter. And that means that the probability of having D4 as the 4th word is only conditioned on D2 and D3, not on D1. And then finally P stop, because we have to at some point decide that the document is over. Who understands this formula, right? And all the assumptions, right? Okay, very good. Now this parameter that here is set to 2 for the Markov rule, it can be changed, right? I can set it to 3, I can set it to 4, but I can also set it to 1 or even to 0. And in fact, if you set it to 0, interesting things start happening. So now, regarding the terminology, notice that if I set it to 2, as in done on these slides, I'm basically having a sliding window of 3 words, right? I always look at 2 words and then the next one, so I look at 3 words at the same time. For example, 2, 3, 4 in the last probability. So now if we set n equals 1 for the Markov condition, then we have by words. We look at pairs of words. And if I set it to 0, then we look at 1 word at a time. We just look at the probability of 1 word, but we don't even look at the past at all. And this is the reason why when we set it to 0, it's called the unigram model, right? So it basically means that we only look at 1 word at a time. We don't even know what the past was. We just keep rolling a die. And so that means that the probability for the next word, so now I'm at position k, so the probability of the next word to be a specific dk is in fact not going to depend on the previous word. So it means that it's the probability of the next word being decay, just conditioned on the fact that there exists a word at that position, so that the length is at least k, right? So what you see here is just a Markov condition, just with n equals 0, right? For everybody is clear? All right. And so in fact, the advantage here is that everything becomes much easier because you don't even have to condition on former words. So it means that all we need is an assignment of every word to some number. It's one-dimensional, right? We just have a list of the words and we have a list of their probabilities that do not depend on the past. So I gave an example here with to be or not to be. That is the question, so 0.3, 0.2, 0.1, and you just want all of these to sum up to 1, right? So it's a probability distribution on the word, and you use that to multiply whenever you want the next word. This is called the unigram model when you do that, but there is more. I will go through the specifics because the unigram model is very, very particular compared to bigram or trigram. You might remember from last time that I started with finite automata, and I explained that we just reverse an automaton by, instead of consuming words in order to accept them or not, we generate words. So we just inverted the use of the automaton. And so it means that we basically have an automaton with just 2 nodes, and one node just keeps generating the next word with a specific probability, and then every time you have the p stop, and then if you stop, then you go to the sink and not to the sink, sorry, because you accept it. You go to the final state where you accept the words. One small word of warning, if you look at it from the automaton perspective, is that we separated the probability of getting the next word from the probability of stopping, right? So there's 2 ways of looking at it. Either you let all the probabilities for the words stop to sum to 1, and then you multiply, you renormalize with p stop or 1 minus p stop, or you put the p stop as an additional possibility, right? And typically when you draw the automaton, in fact, you might renormalize a little bit by actually multiplying all of the weights with 1 minus p stop, and then stop is p stop. And that way it sums up to 1. All the transitions from the automaton sum up to 1. Now, for the really, if you want to really go into the details, what we would have, in fact, in the transitions in the automaton would be here, all of the words, and here that would be epsilon, right? Epsilon is the empty word, so you have a transition with epsilon where you don't have any additional word, and you end up in the final state, right? Also, just to repeat something to make absolutely sure that this is clear, when you look at the regular expressions and finite automata, the labels on the transitions are letters, right? So you have the letters, you consume letters, and every letter goes to the next transition. Or if you generate, you would generate letter by letter. But here there is a subtlety, is that the letters of the automaton are in fact the words in our information systems, right? So the alphabet of the automaton is in fact made of the words of the information retrieval system, right? It's a subtlety, it can take a bit of getting used to, but this is why I have these full words here, to, be, or not, which are in fact letters of the automaton alphabet. For whom is that clear? Right? Okay. So this is the unigram model, and all I need is a lookup table where each word corresponds to some probability. So now, can anybody tell me then what would be the probability of generating exactly the document D1, D2, D3? D1, D2, D3, they're small d, right? So it means it's just mathematical variable. They could stand for any words. For example, it could be information retrieval lecture, right? D1 is information, D2 is retrieval, D3 is lecture. So what is the probability of generating these documents with the unigram model? And in this order, right? D1, D2, D3. Remember, it's the chain rule. It's exactly the chain rule we've seen before. exactly the same things we multiply, except that now we don't depend on the previous worlds. So what could that be? Knowing that we have some lookup table, right? So we have one probability for D1, a probability for D2, a probability for D3. Anybody wants to try? Yes, I see a raised hand here. Maybe you can bring the microphone.
Well, it's just 1 minus p stop for the 3 words, then p stop at the end, and just pd1 times pd2 times pd3.
Exactly. Yeah, you got it right. That's exactly what you said, right? So indeed, it's exactly the same idea as before. 1 minus p stop, then pd1, then 1 minus p stop, then pd2, then 1 minus p stop, then pd3, and then p stop. And now you just see that the probabilities of I will manage it. The probabilities of generating specific next word, now they just don't have any conditions anymore. They just depend on a word. And I just use the notation PD1, PD2, PD3, but PD1, PD2, PD3, these are just the numbers that you have in this table right here, right? So P2 would be 0.3, PB would be 0.2, POR would be 0.1, and so on, right? Is everybody with me? It's going to get more complicated, right? So I'm basically careful. All right. So now here's how it gets more complicated. The probability that you see right here on the screen is the probability of generating documents D1, D2, D3 in this order. D1, D2, D3, not D2, D3, D1, D1, D2, D3. So there is a list of word semantics, and it has to be in exactly this order in the way we generate it. But something is particular to the unigram model that doesn't exist with the other higher values for the Markov condition. And it is that for the unigram model, we actually like to look at it from a bag of words perspective instead of a list of words perspective, right? So it means that when we ignore the past and look at the words one by one, we actually don't care about the order. We only look at the number of occurrences. Now that should remind you of something because we've been doing that in the vector space model, right? In the vector space model, we also ignored the order. We just looked at the term frequencies, so the number of occurrences, and that was it. And so that means that for the unigram model, we need to do a bit of some gymnastics in here to go from having a random document where the order matters to a random document in which the order does not matter. So what does it mean mathematically? So when we have the list of word model, then we have this monoid structure with sequences of words, right? So this is this T star notation that we see, right? So T is for the terms and star just means you concatenate the terms to get a document in a specific order. But if you go to the bag of words model, how do you build the map mathematically? Well, it just assigns every term to some number. That number is the number of times it appears. So a bag is a function from all the words to integers. So n to the power of w, it's a mathematical notation for a function from w to n, right? So we associate every word that there is with an integer. That is the bag of words model. Now, if you look at these two and how you transition from the first one to the second one, on the high level, we just drop the order. We forget the order. And so what that means is that if you have, for example, a document, let's say information retrieval lecture, which doesn't have any order, so it just means that's the bag where information appears once, retrieval appears once, and lecture appears once, and we don't care about the order. How do we relate it to the list of word model? When we relate it in the sense that we look at all the documents, all the possible orders for these three terms. So we have information retrieval lecture, information lecture retrieval, lecture information retrieval, lecture retrieval information, retrieval lecture information, and retrieval information lecture, right? These are 6 possibilities, right? And so now, if I know the probability distribution on every ordered sequence of words in the list of word model, I can infer the probability distribution on the bags by just putting in the same group all of the documents that are basically the same bag, but in a different order. So it means that if I want the probability of information retrieval lecture, I need to, as a bag, I need to have to compute the sum of the probabilities of each one of the 6 possible orders. So the probability with that it's the first order, plus the probability it's the second one, plus the probability is the third one, and so on. Why can I add the probabilities? Because these are disjoint events, right? That's why I'm authorized to add the probabilities in here, right? So actually, all I need to do is a sum. I group all the documents that are just the same bag in a different order. I put them in the same group. And then for that group, I compute the sum of all the probabilities with all possible orders. And I get the probability for the bag, right? For whom is that clear? If it's not, don't worry, I'll have pictures and animations to make it clear. But in fact, this is a multinomial distribution. Who has ever seen a multinomial distribution? Who has never seen a multinomial distribution? That's great, I'll introduce you to it. Who has seen a binomial distribution? That might be a bit more famous, yeah. But the multinomial one actually generalizes it. But we look at the details of that. Here is it. Here it is. That's the binomial distribution. So I thought it was more fun to do it with cats rather than terms, because it's also more visual, but let's look at the details of that. So first, look at the order of the cats, right? So we have here, can I appear on the slide? Yes, exactly. So here we have a specific order. Here it's a specific order, a specific order, a specific order, a specific order. So these are all the possible lists of cats that I can get. How many are there? Possible lists in total with 2 colors. 2 times 2 times 2 times 2, right? So I have 16 possibilities of length 4, if I look at the length 4. Okay, so 16 possibilities, 16 possible orderings, 16 possible sequences of cats where they can be of any of the 2 colors. But things are interesting when I start grouping them. For example, in here, I have the group with actually the only sequence with 4 white cats. Here I have all of the sequences with 1 black cat and 3 white cats that I put together, right? So there's 4 possible orderings, but it's the same bag, right? That's the bag with 1 black cat and 3 white cats. Then I have another group, this time with 2 black cats and 2 white cats, right? And there are 6 possible orderings. Then I have the group with 3 black cats and 1 white cat, it's tongue twister, with 4 possibilities. And then I have the group with 4 black cats, but there's only 1 ordering possible in that case. And so this is what we do when we go from the list of word model to the bag of word model. All we do is build these groups, like here. And so now I can just count, that's combinatorics. I count the number of possibilities. And since it's the binomial distribution, because there's only 2 colors, you might know that formula, right? It's the number of possible combinations with 3 white cats out of 4, right? And the formula for this is 4 factorial divided by 3 factorial, 4 minus 3 factorial, right? N factorial divided by k factorial, n minus k factorial. Who has ever seen this? I'm pretty sure you all have seen it, right? That's exactly the formula. That is the formula for the binomial. N is the number of cats, and k equals 0, k equals 1, k equals 2, k equals 3, k equals 4. And it also corresponds to when you have mathematically a plus b to the power of n, that basically gives you the coefficients also, right? For example, here, that would be 1, 4, 6, 4, 1. And that basically means that if you compute 1 plus b to the power of 4, you will get, is it to the power? I'm always offset by 1 on these things, but basically you will get 1 plus 4, you think? Yes, let me try to the power of 4. If I'm offset by 1, I'll fix it. So basically a plus 4 to the power of 4 is equal to a to the power of 4 plus 4 times a to the power of 3 times b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. And I was not offset, so that's all good, right? So it just corresponds to these developments. So this is the binomial distribution. And now you see how you get from lists of cats to bags of cats, right? And how does it generalize? How does it generalize to more than 2 colors? Well, it's very easy. This formula where you divide with the factorials, you just put all of the numbers of colors at the bottom and the total number at the top, and you just compute that. So for example, this is a bag of cats where there is 3 white cats, 1 blue cat, and 1 black cat. 1, 3, 1. And so you compute the number of possible orderings in there with 5 factorial divided by 1 factorial, 3 factorial, 1 factorial. And that gives you a total of 20, I think. No, 1, 2, 3, 4, 5, 6. Yeah, 20. Okay. Who is with me? Right? So doing that with all of these little cats basically allows us to compute this. Because you might agree that when you look at this formula right here, that computes the probability of getting a document in a specific order, look at this formula and tell me if you agree that the number I'm going to get out of this does not depend on the order. If I compute the probability of D2, D1, D3, or D3, D1, D2, I'm going to get the same number. Do you agree? Just because it's commutative. I'm getting the same number. So that means if I look at this formula right here, that I'm looking at a specific bag, I'm looking at all the possible orderings, but what I'm adding here is always the same number. It's always the same number because it doesn't depend on the order. So do you agree that if I add many times the same number, I can just multiply it with the number of times, right? So what is my number of times? Well, it's just the number of lists that I have in my group. So these formulas here give me basically the number of terms that I'm adding in here, terms in the sense additive term, mathematically, right? So the number of lists that match the bag is given to me with this magic formula or this magic formula, right? So that would be with 3 terms yeah. Okay, who is with me? Very good. So now, surely you can give me the probability distribution for the unigram model, length of 4, so 4 cats with 2 terms. And I have a probability of 2/3 of generating the black cat and a probability of 1/3 of generating the white cat. Can you try to find out the probabilities that we get here? So of course, you need to start with the list of cats model, right? That gives you all the probabilities of generating a specific list. And then by multiplying with these multinomial coefficients, you get the probabilities with bags of cats. Does anybody have any idea how to start? Maybe I can ask a simpler question. What's the probability of generating, let's say, 3 black cats? Yes? Yes, so that would be the numerator and the denominator. So you're very close. So this is indeed about the power of 3. It would be 2/3 to the power of 3, right? So you just multiply 3 times the 2/3 with itself, right? So it's 2/3 to the power of 3. You're absolutely correct. That's the probability of generating a sequence with 3 black cats. Now, since there's only possible ordering, that's also the probability for the bag, right? So we have 2/3 to the power of 3, which is 8 divided by 27, right? But now I have length 4, so it's the probability of generating 4, right? So then I just put to the power of 4, the probability of generating 4 black cats would be 2/3 to the power of 4, right? You agree? And then the probability of generating, let's say, 1 black cat and 3 white cats, exactly in this order, first the black cat and then the 3 white cats. What's the probability of that? That would be 2/3 times 1/3 times 1/3 times 1/3, right? So we just multiply them. So this is what you get. So these are all the possible bags in here, all the possible bags. And now that would be the probability of getting the cats exactly in the order as you see in here, right? So this is here 1/3, 1/3, 1/3, 1/3. This is here 2/3 times 1/3, 1/3, 1/3, getting exactly this order. Then 2/3, 2/3, 1/3, 1/3, we get this. Then 2/3, 2/3, 2/3, and 1/3, we get this, exactly in this order, right? And then 2/3, 2/3, 2/3, 2/3, we get 16/81. Do you agree? Who agrees with that? Okay. You notice it doesn't sum up to 1, right? And the reason it doesn't sum up to 1 is that I looked at the order, and of course, there's other possible orders that are not here. So that's the reason why it doesn't sum up to 1. For example, I could have a white, black, black, white that doesn't appear here. So this is why it doesn't sum up to 1. However, that is the least semantics probabilities, the probability of exactly that order. Now I need a correction factor for all the possible orders that I can get, which I have right here. It's the 1, 4, 6, 4, 1. That's exactly the one we got from here, 1, 4, 6, 4, 1. These are all the possible ordering. I just group them together. So I need the correction factor of my multinomial coefficient. And when I multiply with the correction factor, I get these probabilities. Now, these are the probabilities for the bags. So this is the probability of getting exactly 4 white cats. This is the probability of getting exactly 1 black cat and 3 white cats, but in any order. The probability of 2 and 2. The probability of 1 white cat and 3 black cats, and probability of 4 black cats. Do you see that the probabilities now sum to 1? Because these are the only possibilities. If you don't look at the order, these are the only possible distributions of colors. Okay, who is with me? So we've just linked the list of words or list of cats semantics to the bag of cats semantics. Okay, that's what we've done here. So again, the magic formula for the number of possible orders is this. It's the total number of cats, factorial, divided by the products of the number in each color, right? Factorial. That is the magical multinomial formula. It generalizes the binomial one with n factorial divided by k factorial and minus k factorial, right? And now, if I make one more jump and generalize what we've done with the cats, for the specific cats where I had the 2/3, 1/3 for the probabilities for each cat and a length of 4, it generalizes to this formula. So I'm going to explain it, but if I don't explain it, who already understands that formula? Take a few seconds. I see one raised hand here. Anybody else who already understands that formula? Okay. All right, so I'm going to explain it now. And you will see it's actually exactly what I've already told you. There's nothing new here. I just wrote a formula that does what we did. Look at the product right here. The product right here is basically the probability of generating a specific color, black or white. That's T, that's my term, right? But I have to put it to the power of the number of cats in that color, right? So PT, for example, would be 2/3, right? And I multiply 2/3 for as many cats as there are with that color. For example, here, P black would be 2/3 and P white would be 1/3. And I have to multiply P black here with itself. So it's P black squared, P black cubed, P black to the power of 4. And then P white to the power of 2, to the power of 1, to the power of 3, right? So this is the multiplication we did here. So if I go here, this is this multiplication. So that's P black to the power of the number of black cats multiplied with P white to the power of the number of white cats. Who is with me? Right? So this is the probability for getting in a specific order, right? Knowing that I have a length, a given length. And this here, you recognize, is my multinomial factor. That's the number of possible ways I can order the cats, given the number of colors. So I just multiplied here with, that was the 1, 4, 6, 4, 1 that I get with this, right? So now I'm asking the question again, who understands this formula? right? I see many more of you. Okay, so look at it again, maybe offline, but this is exactly the formula that is known as the multinomial distribution, right? It's the probability of you repeatedly generate cats in specific colors, and then at the end you ask, what is the probability that I generate exactly these numbers of colors, which is the specific bag, right? That is the multinomial distribution. Now, this is assuming that we have a specific length, LD, right? This is a specific length. If I do not know the length, you agree I need to add the p stops and the 1 minus p stops, right? Here I don't have the p stops and 1 minus p stops, right? But if I also want to compute the probability that it has that length, I would also need to add p stop times 1 minus p stops to the power of the number of words, LD, right? And so one more thing I didn't say, because it was probably implicit, is that the TF here is the term frequency, right? It's the term frequency of term T in document D. But do you see that the term frequency is basically the number of cats? So the term frequency, it would be, let's say, a color frequency, right? So that would be the color frequency of blue in a specific document, right? So the term frequency is when I count the cats of a specific color. All right. So this is the multinomial distribution. And here, this is when I add my 1 minus p stop, p stop. So this is the probability. If I know the length is LD, but if I do not know the length, I need to also make sure that I make it stop exactly after LD words. So now, this here is, if I don't know anything, the probability of generating document small d based on the number of terms that it contains. So the bag of words semantics. And every time you see that formula and you're lost again, then go back to the cats. This is how you interpret the formula. So that is the unigram distribution, very, very specific, the unigram distribution, because you do have these bags that you can turn to the bag of word semantics. In the general case, with bywords or tri-words and so on, you basically can no longer do that. Then you have to care about the order. If you say that a word depends on the word before it, then of course you care about the order because you need to distinguish the word that came before. All right. And so what that means, if now I look at the byword or bigram model, then it means that my lookup table, the probability table, is a bit more complicated than the one I had for the unigram model. For the unigram model, it was just a one-dimensional list. But now, in the bigram model, the probability of generating a word depends on the previous word. Do you agree? It means that I'm going to have as many probability distributions as previous words. So for example, I'm going to have a probability distribution if the previous word was 2, and then I get that distribution. Then I have another probability distribution again if the previous word was B, and so on. That is a probability table that contains the probabilities of this conditioned on this, right? Who sees that, right? Who has ever seen a Bayesian network? Right? So you will see Bayesian networks later. That's exactly, so that's basically a smooth intro to Bayesian networks. When you have a Bayesian network, you basically have an arrow that goes from a term to the next term. And this here typically is some transition table that gives you the probability of generating a specific value based on a former value. But don't worry, I'm not going to throw Bayesian networks at you. You'll have a lot of opportunities probably in your masters to learn Bayesian networks. So this is just a lookup table of the probability of generating this term conditioned on the probability of generating this term, and this sums up to 1, and this sums up to 1. No, this doesn't. That's just a typo. It should sum up to 1. All right. Okay, so that is my updated formula. And you see the only difference now that there is with the unigram model is that now I have 2 words in the subscript. I have the previous word and I have the current word. I have the previous word and I have the current word. Here, for the first word, I only have the first word, but that's conditioned on, that it's the first one, right? So that's why it's only one in here, all right? And these numbers here, they're all taken from that table right here. And the first one, the PD1, that would just be yet an additional zone, but it's all empty here. That's when the previous term doesn't exist. And then you have also a probability distribution for the first one. Any questions so far? Who is with me? All right. So that's the probability formula. But now that we've done all of this, you might ask, okay, why are we doing all of this? Why are we generating documents? So do not forget that this is an information retrieval lecture. So we want to search for documents and we want to find documents that correspond to a specific query, right? If I go back to the goal that we have. And so what I'm going to do now is show you a technique, just like we did for the probabilistic information retrieval, the trick with the ELVs and probability of relevance of a specific document given a query. I'm going to give you yet another trick, but based on these language models that we've seen. So imagine this, thought experiment. We are going to take all of the documents of the collection, there might be billions of them, and we are going to ask the little elves in Antarctica to generate a model for every one of these documents. How do you do that? You look at the term frequencies statistically. So what are the distribution of terms in every document? And out of these statistics, you turn it into a probability distribution, right? So for the unigram model, it's easy. You just take the term frequencies and renormalize with the length, and then you get a one-dimensional probability distribution. Now, if it's a bigram model, it's a little bit more involved, but still it's easy. Just a few lines of Python, right, for doing that. You just scan through the bywords and you generate your conditional probability tables based on the term frequencies or the frequencies of the pairs of words. So basically, you generate a model for every document. So that means that every document gives you a model, and you can then use that model to generate new documents that look alike, that look like the first one, just statistically, because the probabilities were taken from the frequencies in the documents. So we do that for every document. In fact, it's quite fun to do. So now, of course, now that we have LLMs and ChatGPT, it's a bit less impressive, but back then it was impressive. I think the first time I saw that was in the 90s, but it was probably even before that. That without LLMs, just looking at the term frequencies or the frequencies of pairs or triplets and so on, and building models like that, you can just generate documents. So for example, with 1 grams, you just look at the term frequencies, unigram model, and you just toss a coin for every word, but without looking at the past. And you get something like, to him swallowed confess here, both which of save on trail for RA device and wrote life have, he late speaks, or a more to less first you enter. I didn't get anything of that, but again, that's a unigram model. There is no connection, there is no order. So of course, that doesn't sound very human-generated, let's say. Now, if you go to a bigram model and you look at now the 2-word windows and you generate the conditional probabilities. So again, you look at the term frequencies, but conditioned on the previous term. And so if you try to do that and you build this probability table right here, based on the frequencies that you have in your documents, and you do it with Shakespeare, then you come out with why does stand forth like canopy forsooth, he's this papal hit the King Henry, leave king follow, what means sir I confess sheed, and all sorts he is stream captain. So now you see it still doesn't mean much, but you still see a connection between the words now, right? You still have the feeling that a word follows another word in a more logical way. Then you do it with 3, fly and will read me this news of price, therefore the sadness of parting as they say it is done, this shall forbid it should be branded, it renowned made it empty. So now we are getting closer, right? It starts sounding, you still don't get what it says, but at least it starts sounding a bit like it's making sense. And then you increase 4 grams, King Henry, what? I will go seek the traitor Gloucester, extend some of the watch, a great banquet served in, it cannot be but so, right? And imagine there were no LLMs, right? Decades ago, we were doing that, it was quite fun, and you actually get texts that kind of sounds natural. And you could also do it with music. I remember who read Gödel Bach? Douglas Hofstadter? Nobody, you should read it. Gödel Bach, he got the Pulitzer Prize with that book. It's about the Gödel theorem and theoretical computer science, let's put it. But it's really a masterpiece. So Gödel Bach. And the author of this book was giving talks where he was generating music. So instead of words, he was doing it with music notes, and he took Bach, all the composition by Bach, and then he just created a model and generated music, and it just came out. Then he made a vote, like who thinks this is the Bach piece, and who thinks this is the piece generated by the model. And a lot of people got it wrong. That was before LLMs. Now we do that, of course, with more mature models, which is much more precise, and it fools us even more than it used to. But yeah. All right, so you see, this was pre-ChatGPT, pre-LLMs that we could already generate with quite simple code. You can really, I'm pretty sure you can do that in 1 hour. You sit in front of a computer, you take Shakespeare, Sherlock Holmes, you can program that in 1 hour of your time, pretty sure. Who feels they could do it? Right, many of you, right? So it means you understood, all right. Okay. So now, of course, we have the luxury of having ChatGPT, and a lot of things change. And now they actually, it seems, pass the Turing test now, because we can no longer tell them apart. So that was ChatGPT 3.5. This one I actually managed to fool, because it actually came with a definition of Weltschweizerdeutsch. Deutsch. But ChatGPT 4 cannot be fooled anymore. Right now, it actually has a bit more, I wouldn't call it reasoning, but was a bit more powerful. Okay, and it seems that the new one actually again got fooled. So I think there was here a bit of a loss with 4 compared to 4. That this one actually again got fooled. But anyway, you see the evolution, right? This is really decades and decades and decades of evolution. And for this, the LLMs, you will need to go to the LLM lecture when it's offered, and then you can learn how we actually can build these things with the modern means. But coming back to my information retrieval system, now I have these documents. I generated a model for every document, and that model is able to generate new documents. So now here's how I build my system. The user just wrote a query in the website, in the query box. They wrote a query that I'm going to call Q. Now, imagine for a thought experiment that we picked a document at random. In the library, there's billions of documents. I picked one at random, uniformly, and I built its model. And I generated a document out of this model. And now you won't believe it, but what I generated turns out to be Q. I was lucky, I just randomly generated Q. And knowing that I told you that, I picked a random document, turned it on, ran a generation of a document and happened to find Q, as unlikely as it seems. Then I'm asking you the question, given that, what do you think was the document I chose? What is the document that is the most likely to just so happen to generate Q, right? The highest likelihood. That is the thought experiment. So of course, we cannot do that in reality, right? Except with our elves in Antarctica, they can generate them for all the documents. But again, it's a thought experiment. So now we have a problem that we need to condition on a query Q, find the document the most likely to have generated it. That is complex. In fact, that's just like asking if I have my umbrella, what's the probability that it's raining, right? And what do we do when we have a complex conditional probability to compute and it's too difficult? What do we do? Who knows? I will not ask, but who knows what we do? Okay, let's take the break. You can think about it. I'm pretty much sure you're going to guess that. So let's take a break, and in 15 minutes, I'm going to tell you the solution, right, of how we compute this, the likelihood of a document to generate a query Q. So see you in 15 minutes. Thank you.